Hi, just a quick video here to look at the simulation of a single transistor common source amplifier to maximize its gain and bandwidth. So you see here a simple test bench setup. Got a single transistor common source device here. It's being biased by a constant bias current source, 500 microamps. So if that were coming from, say, a 1 volt supply, then we would be consuming half a milliwatt here in this circuit. But since it's an ideal current source, I just have it coming from ground. So it doesn't really matter where it's coming from since it's an ideal current source. I have these components here just to bias the gate at an appropriate voltage that keeps the transistor in saturation. And here's the AC source driving the gate. I've got here a 200 femtofarad capacitive load on the drain. So what I've done is I parameterized the transistor width here, and I'm using a minimum gate length of 45 nanometers. So we're going to run the AC simulation here where we sweep the width of this device, keeping, again, the bias drain current constant. So as we increase the W over L ratio of this transistor, what will happen is we'll be decreasing the effective gate source overdrive voltage, but all the while keeping a constant power consumption. So let's take a look at how the simulation's set up here. Got an AC simulation. We define the frequency range here, and we're doing a parametric sweep here on the transistor parameter width, and I've set a bunch of values for the sweep here, everything from 1 to 1,000, and you'll see that those width numbers are multiplied by 1 micrometer, so we're going from essentially 1 micrometer to 1,000 micrometer device width here. Okay, so let's go ahead and run the simulation, see what happens. Okay, so we got a family of curves here, and representing all the different transistor widths in the list. You'll see that the narrowest device resulted in a lower DC gain for this amplifier. So the reason is that the V effective in that case is a little bit too high. We're not maximizing the transconductance for the given bias current. In order to do so, we want to have the transistor bias kind of on the verge of subthreshold operation. So as we increase the transistor width, we see an increase in the DC gain, and the bandwidth of this circuit is ultimately determined by GM over the load cap, which in this case 200 femtofarads, in parallel with any parasitic capacitances associated with the transistor. Now the 200 femtofarad capacitance is dominant in this case, so increasing the device width simply increases GM, gives us both more gain and more bandwidth. And we see the trend continuing to higher gate widths, reaching this maximum here of, a gain of something like 5.6, 5.7 volts per volt. So that's about the most gain that we can get from this transistor. So that's sort of the maximum intrinsic gain for this transistor. It's a modest gain, only about 5.5, as we might expect from a nanoscale CMOS transistor with a very short gate length. Now you notice something interesting. If we continue to an extreme and increase the transistor width to a very high value, we don't lose DC gain. That's because the DC transconductance is still there. In other words, in subthreshold, the DC transconductance has become constant. So we get no further increases in DC gain, but we do start seeing a reduction in bandwidth because now the transistor is so large that its own intrinsic capacitances are comparable to the load capacitance, 200 femtofarads. And so we've now got effectively more load cap and but no extra GM. So we're starting to lose bandwidth. So somewhere in between, we maximize everything here. Here we've got the maximum bandwidth and maximum DC gain for this particular case. Thanks for listening.